Welcome to the estimation unit. In this video, we will make the introduction on what is estimation. So in general, this is a branch of statistical inference in where the idea is that you want to make an inference about a parameter. So an estimation, you might imagine that you want to find what is the mu, for example, what is the mean value of a population. So for that purpose, you can make an estimation. This is one way with using X bar. So based on a sample, you can measure the sample mean, which is an estimation of the parameter, right? So there are different ways to make the estimation. One is what we call point estimation. That means getting a single value. That's why it's called point estimation. So if you want to make an inference about any parameter, so using a metric based on the sample, that will be a point estimation. And of course, you want to minimize the distance between the parameter and the estimation that you're making. There are a couple of methods that will help you to perform point estimation. Some of them are method of the moments and the maximum likelihood, but those methods are not covered in this class. We will focus more in the second approach, which is an interval estimation. That means that instead of trying to get a single number, sometimes it's better to use an interval. An interval with a lower limit and an upper limit. And of course, those lower limit and upper limits will be estimated using the sample information. Now, there is an important concept here when we define these limits, this confidence interval. That's what we're going to call them, confidence interval. And the concept that is critical is what is the confidence level. The confidence level here refers to the probability that the parameter is included in the interval. It's 1 minus alpha. So this is what we call the confidence level. And alpha will be the level of significance. Level of significance. Alright, so usually you will see 1 minus alpha to be equal to 95% or 0.95, 99%, and in some cases 90%. So to start the popular confidence level that are defined, especially 95%, I would say is the most popular one. Then once we get our confidence interval, once we have estimated the lower and the upper limit, we always claim that it was built using a confidence level of 1 minus alpha. And of course, the lower and upper boundaries are considered the confidence limits. Now, how can we use these intervals to perform some estimations, especially if we're talking about the mu, sigma, p, or even means differences, a ratio of sigmas. So that's what we're going to analyze now, the cases. So these cases are connected with those cases that we cover in the sampling distributions unit. They are pretty much the same cases. So the first part we will cover the mean cases. So mean case 1, remember, is when the data comes from a normal population and the standard and the variance is known. We know sigma squared, right? Then the confidence level is defined as 1 minus alpha, and of course we can create a confidence interval using the normal distribution. So based on the assumptions, the sampling distribution will be the normal distribution. That's why if you check the equation, we have z. So let me get you a better idea of what's this. So this is pretty much normal distribution, right? And we're trying to get an area here. If you notice, we have x bar plus minus, right? And then we add and remove z, alpha divided by 2. What is alpha divided by 2? So the region in the middle, the inner region between the limits, that's 1 minus alpha, right? Therefore, what is left to the right and to the left, this region and this region, the area of those regions is going to be alpha divided by 2 and alpha divided by 2, right? So when we're getting the lower limit, so this will be, the estimation is going to be x bar minus alpha divided by 2, z of alpha divided by 2, and of course times the standard deviation, so that will be sigma over the square root of n. And the same idea applies to the upper limit, but here instead of the minus sign, it's with the plus sign. So this is how we get those boundaries, right? This is how we get the confidence interval. Remember, first you need to define the confidence level, the 1 minus alpha. In addition, you need to identify which case is the one that you're going to use. So in this case, we can approximate to a normal distribution, therefore z can be used in the equation. Alright, so the confidence interval, what is the interpretation? So it just means that using sample information, if you create like multiple confidence intervals, right, as you see here, this is the true value. This mu here is the true value. It's the parameter that you want to estimate. So the confidence level means the percentage of times that the confidence interval is going to include that parameter. So if you're defining the confidence level as 95%, so the idea is that 95% of the times that mu is going to be included in the interval. So in some cases, like in this one, it's not included, right? You never know that, unfortunately. I mean, from the beginning, you don't know that because this is statistics, so that's why we define the confidence level. Alright, so in case 2, for mu, we want to estimate mu using x bar. Case 2, it's when the data is not normal, so it doesn't come from a normal distribution, but n it's high, it's greater equal than 30. So remember the central limit theorem. So using that principle, we can again approximate using the normal distribution. That's why again we have z here. And in those cases where we cannot approximate the normal distribution, if we are trying to make an inference of mu, we'll use t, right? Remember the t student. So cases are the same as in the sampling distribution units. So let's check an example to practice a little bit what we're learning here. The average zinc concentration recovered from a sample of measurements taken in 36 different locations, that's our sample size, is 2.6 grams per milliliter. So that's an x bar, right? That's based on a sample of 36 observations. That's a sample value. So we want to find two confidence intervals, one for a 1 minus alpha of 95% or significance level of 5%, and the other one for 1 minus alpha equal to 99%. Assume that the population the standard deviation is 0.3, so it's given, is known. Alright, so we have sigma equal to 0.3. Okay, so we're gonna use the normal distribution in this case. Therefore, let's use the equation for the first interval. So it's x bar, that will be 2.6 plus minus, so 2.6 plus minus, now we need z, right? So for the first part, we need to find, remember, so let me show you again. If the confidence level is 95%, that's 0.95, then what is left to the left and to the right, all of that it's 0.05, right? So in this case, this is 0.025 and 0.025. So we need to get z that has 0.025 25 to the right, or if your table goes to the left, or if you're using software, then you need z with an area to the left of 0.975, right? The z here will be the same as the one in the lower limit, but the only difference will be the minus sign, right? That's why we have here the minus, the plus minus. So using the same z value, in this case z is equal to 1.96. If we go to your tables and find z for these areas, either to the right or to the left, you will get the 1.96 times the standard deviation, that's the 0.3, over the square root of n. So we can compute these values, and we will get that the lower limit in this case is 2.502, and the upper limit is 2.697. So what is the interpretation of this limit? It says that with a confidence level of 95%, the parameter it's between 2.502 and 2.697, right? So imagine that someone is asking, is the true parameter equal to mu equal to 2.8? Imagine that someone is asking about this. It's not included in the problem, but imagine that someone is asking, is the parameter, the true parameter, equal to 2.8? Since when you find the confidence level, that value is not included, so you will say that with a confidence level of 95%, we can reject that claim, right? That mu is equal to 2.8. Why? Because it's not included. Now, if someone is asking that if mu is equal to 2.6, 2.6 is included here, so you won't reject that idea. All right, so using the same idea that we just did, we can find the confidence level for the 99%. The only change will be z. So instead of 1.96, now the new z value is going to be equal to 2.57. So once you do that, of course your confidence interval is going to get wider, because with the 99%, that's a wider area. So in this case, it's 2.57 mu is equal 2.72. So there is a trade-off here, because maybe you're thinking, okay, I want a higher confidence interval. That's nice, but the problem is, like, as the higher is the confidence level is higher, then the wider will be your interval. Therefore, your estimation is going to be less accurate, because in general you would like to have a narrow confidence interval, but of course you don't want to affect the confidence level. So we want a mix of them. We want like a good balance between high confidence level, but at the same time you want a narrow confidence interval. Why? Because you want to make a good estimation. So the narrower, the better will be your estimation. Okay, so in the same way we have case 3, but now in case 3, data comes from normal distribution, but here the variance is unknown. So we assume typically that this case is for small samples, so we cannot approximate to a normal distribution. That's why we're using the same equation. Instead of sigma we have s, and of course instead of z we're using t, which is for the t student, and of course you require degrees of freedom to find those values of t. Case 4, so if the population is not normal, but the sample size is large, so in that case, a squared is a good estimation of the variance. Therefore, we can approximate to the normal distribution. We can use z. That's the important part. All right, so let's solve this problem. A company suspects that the water consumption levels have decreased in a neighborhood. The historical average consumption per house is 20 cubic meters. The fraud detection area collects information from 121 houses and finds that the sample average consumption is 19.1. That's X bar based on the sample 19.1. The historical value, so this is like a parameter, right? It's 20. We want to check that if the sample information it's like aligned with the historical consumption. So we know that the standard deviation of the sample is 4.56. So using a confidence level of 95%, analyze the company's if the company's concerns are justified. So 1 minus alpha, it's 90.95. So the question here, okay, you took a sample, it's 19.1, so you want to check if the true mean is still 20. If there is fraud, you want to check that. So what we're doing here is that we're going to build the confidence interval, and we're going to check if this 20 is included in the interval. If it's not included, then maybe you can start claiming that there may be something fishy, something wrong about the current consumption levels. So let's create our confidence intervals. So for that purpose, even though we don't know the sample mean, it's unknown because this is sample information, right? S equal to 4.56. Please note that we have a large sample size, which satisfies case 4, right? High n is greater or equal than 30, therefore we can approximate to a normal distribution. So let's do that. I'm going to create the lower and upper limits for the confidence interval. So X bar 19.1 plus minus. Now we need the Z value. Remember, if the inner area is 0.95, then we need Z that has an area to the right of 0.025. Same thing as in the last problem. That Z value is equal to 1.96. 1.96 times S, which is the sample standard deviation, 4.56, over the square root of n, 121. So we can create then the confidence interval, right? So we know that it goes from 18.28, so the mean is included 18.28 and 19.91. So with a confidence level of 95%, based on the sample information, it is expected that the true value of the parameter, right, it's between 18.28 and 19.21. So now if we want to answer the question, please notice that mu equal to 20 is not included in this confidence interval. It's out of the limits, right? And that means that the consumption right now it's below that value, right? It's below the 20. It's below the 20 cubic meters. Therefore, there is a high chance that there is some fraud right now. It looks like there is some fraud right now because the parameter most likely has decreased according to our 90% confidence interval. So there is a high probability that that someone committed fraud with the water consumption. Maybe they're using a magnet or I don't know what. Okay, let's check the last case in this video. It's the confidence interval of the variance. So there is only one case in this analysis. So our data has to come from a normal population, and if we want to create the confidence interval, remember that when we're using X bar or mu, we use normal or T student, right? But every time you're going to analyze sigma, then the probability distribution that we use is chi-square, right? That's for a single for a single population. Alright, so then if we want to create a confidence interval for the variance, then it will use, of course, the population the sample variance S square, and the chi-square, which is the statistic that is used in these cases. Alright, in the terms of the degrees of freedom, it's n minus 1, and of course be careful with the areas. Here this one has to the right an area of alpha divided by 2, and this one has to the right an area of 1 minus alpha divided by 2. So let's solve this problem. It says that a manufacturer wants to evaluate a machine ability to fill bags with beans. The population standard deviation is 0.02. So sigma equal to 0.02. A sample of 20 bags is collected, n equal to 20. And we have the following table, right? We have sample information. Now, using the sample information, it is possible to estimate the variance value. The variance value, S squared, is equal to 0.000578. That's the sample information, right? Now, the question here is analyze if the sample variance is equivalent to the process defined variance. So we know sigma of the process, right, the parameter. So sigma squared, it's 0.0004. So we want to check if, based on this information, the sample information, this is true. If sigma squared, it's actually 0.004. So what we're going to do is let's create a confidence interval. That's our estimation of the parameter. And then we need to check whether the 0.004 is included or not. If it's included, then we can claim that it's true. They are equivalent, right? But if the true value is not included in the confidence interval, then you will have a suspicion that most likely is not true. It's not following the guideline or the historical value. Alright, so let's create our confidence interval. So it's n minus 1, that's 19, n minus 1, divided by, and times S squared, that's 0.000578, divided by Z, this is the chi-square value that has an area to the right of 0.025. So if you find that value, it's going to be equal to 32.85. So remember, you can do it using the table or Excel, it's up to you. So this is 32.85. And the upper limit has the same numerator. It's 19 times S squared, 0.000578, divided by, now this is chi-square, and the area to the right is 1 minus alpha divided by 2. So that chi-square is 8.906. So if you compute these two values, you get that sigma square is between the lower limit 0.30, 1, 2, 3, 3, 3, and the upper limit is 0.20, 1 and 2. And of course, now let's answer the question. So let's check if the parameter or the population variance sigma square which is 0.004, is included or not. So if you check that value of 0.0004, it's above the lower limit, right? 0.003, and below the upper limit, which is 0.001. That means that the parameter, that the value, it's included in the confidence interval. Therefore, the answer here is that the sample information confirms that the true variance is 0.0004, right? That's with a confidence level of 95%. We don't have reasons to be suspicious about the values that we're getting. Okay, guys, this is everything in this video. In the next part, we will continue talking about confidence intervals in the remaining cases. I'll see you in the next video.